All right, moving to the 6.5 here. 6.5 is going to be another one of those big sections that it's going to take us a few videos to get through. But section 6 should be fairly small, and we'll be finishing up chapter 6 and getting ready for the chapter 6 test here. So 6.5 is kind of broken down into two different things, force and work. So these two things are related. I'm sure you guys have been taking physics along with your math classes here. To find the work, if you're given the force, there's two different things that you have to worry about. If it's a constant force, then the work is just taking the force and multiplying that by the displacement, or the distance, I guess you can think of. So as long as it's a constant force, just take that constant force and multiply it by the distance that you're applying that force. So you'll probably have like maybe one or two quick questions on the homeworks about this. And it's very simple. Just multiply those two things together. You do not have to worry about vector stuff for this course because we're only doing like one-dimensional stuff. So just multiply the two numbers together. Where things get more difficult is when you have a variable force. And there's a bunch of different examples that we're going to look up, but the first type of example we're going to look at is spring examples. So depending on how stretched out you have the spring, there's going to be a different force that's applied on a weight on the end of that spring. So there's not really like a simple formula for this yet, but we're going to come up with it here. So coming up with a simple formula for work with variable force. Okay. So think about a number line. And let's say you have some kind of weight located at A and you want to move it to B. Another way to think about it is the spring. Let's say you have a spring that right now is ending at A and you want to stretch it out to B. Well, the force to do that would change as you move from A to B. So if we want to come up with a formula to find the total work moving from A to B, we're going to do what we always do, and we're going to partition this into n different partitions. Instead of looking at like the force going across the entire object, let's just look at the force moving from one value to the next. Let's say we're going from here, x sub k minus 1, to here, x sub k. It is so hard to draw on this little thing here. Okay, you know what it says, right? X sub k minus 1 and x sub k, and we're just looking at the work to go from here to here. Eventually what we're going to do is we're going to do what we always do and make the number of partitions go to infinity, which is going to make this distance in between the partitions be infinitesimally small. So small, in fact, that we're just going to assume that the force to get from one partition edge to the other partition edge is constant because these two things are so close together, the force can't possibly change that much going from one to the next. So if the force is constant, moving from one edge of the partition to the other edge of the partition, then we're going to say that the work located at that particular partition comes from the constant work formula. So just the force being applied at that particular partition times the distance here, and that distance we're going to label as dx, right? That infinitesimally small distance. That's just the work at this one location. Then if I want to find the total work, we're going to do what we always do. We're going to take the limit as n, the number of partitions goes to infinity, which is going to give us the integral. So when you have a variable force, the total work is going to be the integral from the first location to the end location of integrating over the force as a function of x dx. Okay, so with variable force, this is going to be the formula that we're going to use. All right, so I'm going to go on the next page here, and we're going to do an example with a spring here. I'm just going to go over to the book. Let me find my example. I guess another thing that we need is Hooke's law. I hope that you've seen this in physics before. So with a spring, the force that's being applied by a spring is the spring constant times this x, where this x is the distance from what we call the unstressed or the natural length of the spring. All right, so this is going to be the first example we're going to do here. Find the work required to compress a spring from its natural length of 1 foot to a length of 0.75 feet if the force constant is 16 pounds per foot. So let me go back over to my stuff here. We're going to write out basically what we have here. So we have a natural length of 1 foot. We're going to compress it to 0.75 feet, and then our spring constant 16. So natural length is 1 foot. We're going to compress to 0.75 feet, and then that spring constant K was 16. Okay. You just have to be a little bit careful when doing questions like this, especially when it comes to setting this up. So let's think about our X and Y axis here, and let's think about the spring. Usually the easiest way to do these questions is to have the spring's natural length end at the origin. So if we have a spring that has a natural length of 1 foot, we're going to go out to 1 foot, but this is going to be where the spring is anchored. It's going to be anchored here at 1, and then it's just going to stop here at 0, where this is the natural length. Then what we're going to do, right, is we're going to compress this and push it to the right in the positive direction so that it's only 0.75. So if it's still anchored here at 1, we're going to make it so that it's compressed to here at 0.25. That way it still has that length of 0.75. That means to find the total work, to do that, we're going to integrate. My natural length started at 0, but now I've moved the end of the spring to 0.25. And we're going to integrate over the force of the spring, which is coming from Hooke's law. Remember Hooke's law, the force is equal to K times X. So our K is 16. We're just going to integrate over 16X. This has antiderivative 8X squared. That's being evaluated from 0 to 0.25. Plugging 0.25 into this, we get, I think, 2. And this was the work. Work for us is going to be in foot-pounds. So this is the American metric system, foot-pounds. If we were in the other metric system, that would be in joules for our work. Just to double check, make sure I did that math right. Of course I didn't. Plugging 0.25 into that, it's 0.5, not 2. That's what I get for doing it in my head. 0.5 foot-pounds. Okay, great. Good. So I'll probably end the video here just for that. This is variable force, or when you have a variable force, you integrate over that variable force to find the total work. Probably the most difficult part of it is just setting it up correctly so that you get the limits right. With springs, it's almost always easier to do it so that the natural length starts here at 0.